This is my downhill bike, a YT Tues. It has a custom rear suspension that I've built to solve some issues that I had with the original setup. Let's jump right in. This is what the original suspension looks like. My main problem is that I weigh around half as much as Cam's Inc. or Aaron Gwynn. The Tues is a fantastic bike and the original suspension works great for those aces. But the original rear suspension cannot be set up correctly for people that weigh less than 60 some kilograms. There are no coils available with spring rates less than 200 pounds per inch or 36 kilograms per centimeter. But 200-pound springs are far too strong for my weight. I get less than 20% sag even with all my body armor on, instead of the 30 to 33% that I would aim for. Sag is the percentage of travel that is taken up when you just sit on the bike. It is more when you have body armor on because you weigh more. For downhill, you usually want around 30% sag. This is what 15% sag looks like, which is far too little. And since those 200-pound coils were the softest ones available for any 10.5-inch shock, they were at the very edge of the damping force range of the dampers in the shock. If we would make a softer coil for the shock, it would be overdamped. That means that especially the rebound damping forces would be too strong for the relatively weak spring, preventing it from extending fast enough after it was compressed. This is also the reason why it would not help to just replace the coil shock with an air shock. I would have to adjust the air pressure very low to get the right amount of sag, and then the damping force and the friction of the seals would be far too strong in relation. I had that problem before with another bike. Once I had adjusted the air pressure for the right amount of sag and got off the bike, the shock took forever to get back up. That looks almost comical. So that was no option. I needed a different solution. I started with the virtual model of the Tues' rear suspension. Let's take a look. At this stage, only the trajectories of the articulated joints and of the rear axle are relevant, so there's no need to replicate the exact shape of the tubes and stays. The model shows that the rear suspension of the Tues is more progressive than those of most other bikes. The ratio between wheel travel and shock travel increases by about 50% between the beginning and the end of a full compression. That makes the suspension compliant over small bumps but still leaves reserves for strong impacts. I like this layout and wanted to keep the principle in my setup. I use the suspension calculators to confirm my calculations that a shock with 63 millimeters or 2.5 inches of shock travel should work perfectly for what I needed. These shocks usually have a length of 216 millimeters or 8.5 inches between the eyelets. Since the Tues' original suspension setup is designed for shocks that are 267 millimeters or 10.5 inches long, using a different shock size would require significant modifications. This is one of the models that I used to test different possible geometries for my own suspension setup. It worked perfectly, so I refined it until I ended up with this. This sketch was the basis for the CAD model of the link, which I also programmed in Fusion 360. This is how that process went. I sped it up just a little bit. Yeah, you know I'm lying. This is a simulation of a botched landing from a 3-story building. In the lower right corner, you can see the scale that is used to visualize where the stress is in the model. The dark blue indicates the least stress and the red indicates the most stress. If you turn it down to the greens and the reds, you can see the greens, yellows, and the reds, you can see where most of the stress is. These arrows indicate the forces that are put on the link. These two arrows are the forces from the wheel. These two forces are the reacting force from the rear suspension. This is a torsional force, and this is a side load. The torsional force and the side load don't usually happen, but I really wanted to torture this thing. In the displacement, there is always a blue and a red, and the red does not mean that it is badly displaced. It just means that it is the most displaced area of the model. You can see that it is red because there are a lot of forces acting on this area, thus making it the most displaced in the model. Here in the front, there are no forces acting on this area, making it the least displaced area of the model.
The stress simulation went great, so I went ahead and printed a 3D model. Here it is. I also made a model of the shock, but I printed it without the piggyback because we don't need it here. I used this setup to check fit and clearance. This is the full range of travel that the shock will experience when you ride the bike.
The next step is CAM programming. CAM stands for Computer-Aided Manufacturing. In simple terms, CAM software analyzes the CAD model that you have programmed and creates a file that tells a computer-controlled machine tool how it has to move to create the shape of your model from a solid piece of material. The program files for the suspension link had more than 1 million lines. The maze of lines that you have seen before showed how the tools will move for this part of the milling process. This here is now the simulation of what the result of these moves will look like. First, I use a 10mm mill with a square end. It can remove material pretty fast, but it's not good for 3D shapes and tight corners. That's why after the square 10mm, I'm going to use a 6mm mill with a round end for the 3D shapes and to get into the edges of the cross braces.
So far we've milled this out of this. We milled it so that we could have perfectly square edges and perpendicular sides. The amazing thing is, this part is already in here. The problem is you just can't see it because I still have to remove around 90% of this material.
The material is aluminum 7075 T6. This is what the part looked like after I had milled it from the first angle. The main challenge during this build was getting the part clamped in 7 different positions with the tolerance of less than 0.03mm along all 3 axes. That was pure torture. Please don't judge my CAM and milling skills too harshly. I know that, for example, the feeds are very careful, but this is the first milled part that I ever did that goes beyond round holes in aluminum and notching steel tubes for the chassis of our carbon fiber autoclave. The new geometry and the reduced shock length increased the load per inch or centimeter of shock travel by about 65%. With the original setup, I would have needed a coil with a spring rate of around 135 pounds per inch. With the new setup, the equivalent spring rate would be around 225 pounds per inch, and that's well within the optimal working range of most shocks. The new suspension allows for perfect setups for riders with a weight between 40 and 70 kilograms. The new link is even stronger than the original one, but the whole setup is around 700 grams lighter than before. There is a range of good enduro and downhill shocks in the 8.5 inch size. With my low weight, a good enduro shock works perfectly for gravity duty. I got a new RockShox Monarch Plus, but there are other options as well. The new geometry and the use of an air shock allowed me to make the last 30mm of travel very progressive, so that it acts kind of like a soft bump stop. This is actually the last picture that I have of the milled part before it looked like this, simply because I forgot to take any more pictures of the link before it came back from anodizing and I had installed the SKF bearings.
are the original link and the new one in comparison. In the side view, I changed the outline slightly by moving the bends further backwards. The cross struts improve rigidity against side loads and torsional forces. In theory, there should not be a lot of those in the link, but downhill riding can create forces that theory forgot about. And the seat stays provide them with pretty long levers. With the new setup, we now have 30% sag with 145 psi, or exactly 10 bar air pressure.
The new suspension works perfectly. I've tested it at Northstar, and we also plan to ride at Mammoth and Whistler this summer, and maybe some other places. It was an interesting project, but stay tuned for some really radical ones.